are very long-term correlations. Intelligence needs to, for example, remember that if you start a sentence with a capital letter, it needs to remember to finish it with a dot, right? And it's really hard to train such networks, but quite recently people have managed this, and as one of the examples how they can do this is they fed a neural network with a bunch of mathematical papers, mathematical books, let it train, let it read these papers, and then they allowed this network to speak, and you can see the outcome of this neural network. This is a network trained by Andrej Karpathy and is available on his webpage. And this network was trained on a book on algebraic geometry. And I'm not an expert on this field, and as a laik, I would, apart from some trivial mistakes, I would buy that this is indeed something meaningful, right? And the most remarkable thing about this outcome is that it was a TeX file and it did compile. And you can also see that this neural network learned to omit proofs on this book. Okay. So how does it work? Or what is the basic strategy on these neural networks? Because we want to somehow capture the long-term dependencies in the text. So we need to have something which goes very, very deep in as long the sentence goes. So we have a certain input which we put into this network, and this can be either letter by letter or word by word. Then this is processed through this, let's say, network. There is a certain set of parameters which we call weights, and then there is an outcome of this network. This can be a new letter, new word, which network predicts to occur, or it can be or we can feed this network with a sentence in English and get the outcome translated sentence in German, for example. And this network goes recursively in the sense that we not only it processes the input to the output, but also the information that is processed in the network is also sent to the next step of processing, and this generates these long-term dependencies. Okay, so how does it work? We have a set of parameters of this network, which we call the weights. We have a certain nonlinear function. It can be sigmoid, ReLU, or something, and we also have something which we call external input, which is this sentence that we want to translate, and then the outcome of this network is calculated. So this is the simplest possible network that we can consider. Okay, so let us take this equation and let us subtract the value, the previous value the time before, and divide it by 1, which is the time step. So we can see that this is like a difference between consecutive values of the state of this network divided by the time step. You can do something like a limiting procedure and take the time step going to 0, and then this quantity tends to a derivative. So in this sense, we can obtain a set of differential equations which may describe this network as working in a continuous time, and this was one of the motivations to start looking at this kind of networks. Okay, so 30 years ago, this problem was considered by Sompolinsky, Crisanti, and Somers, where they considered the weights of this network as just random numbers. They didn't think about training this. They just wanted to study the dynamics of this network because it's interesting by itself. It's a system of coupled differential equations with some nonlinearities. And they discovered that if all the eigenvalues of this weight matrix have a real part smaller than 1, then the dynamics of the network is trivial because this activity, the values of x, very quickly go to 0. On the other hand, if at least one of these eigenvalues have real part greater than 1, then the dynamics become chaotical, and it is related to the fact that the fixed point, which is at 0, becomes unstable, and we have a transition between this trivial dynamics and the chaotic dynamics. But this network is not very biological, because it's just some collection of random numbers, and the dynamics goes in a very random way. And later, Rajan and Abbott wanted to make this network more biologically plausible, and they insert into this model some heuristics. Namely, they postulated that there are two types of neuron in the minimal model: the neurons which excite other neurons, and the ones which inhibit other neurons. And there is also an observation from neuroscience that if a neuron excites one of its neighboring neurons, it must excite all of them. So the transmitter that this neuron sends to all its neurons that it couples is of the same type. It's either excitatory or inhibitory. There are no mixed neurons. And they updated this synaptic weight matrix in such a way that these parameters are either greater or smaller than 0, and this mean values of these parameters are encoded in this matrix M, and it has a very peculiar structure, because this is a matrix which has columns of the same, when the entries of its column are all the same numbers. But there's also a stochastic part, which is to model the populational variance of neurons. So in such a way they constructed this strength matrix, but there was a problem. When we add this matrix, this M, to the model, then some of the eigenvalues of the initial matrix, they go beyond the unit circle that they were before, and they can have a real part which is greater than 1. And this is something which we don't want, because then the network behaves like a chaotic. So the question is how to cure this model. So they found another biological motivation. Namely, there is a very peculiar balance between excitation and inhibition between neurons, and it turns out that each neuron operates in a very balanced situation, because the sum of excitations acting on this neuron is the same as the sum of inhibitions, and this balance is kept very tightly on the scale of 10 milliseconds. So there must be something behind this. So they imposed these conditions into this model, and in this sense it translates that the sum of elements within each row is 0, both on this matrix of mean activities of this constant connections, and also the fluctuations are somehow constrained. And it turns out that this condition brings these outliers back to this circle, and it cures the problem of chaotic dynamics. So in Krakow, we are somehow very interested in eigenvectors. So we wanted to look more deeply on this problem. So to set the stage, we can say that a matrix is not normal if it does not commute with its transpose, and then it not always can be diagonalized, but if it can, then it has two sets of eigenvectors, right and left. They satisfy eigenproblems from both sides of the matrix, and these eigenvectors are not orthogonal in the sense that right eigenvectors are not orthogonal to rights, but they are bi-orthogonal. So lefts are orthogonal to rights. Unfortunately, these eigenvectors are not unique, because you can always rescale left eigenvector by some number and right eigenvectors by its inverse. So if we want to study their properties, we need to look at quantities which are invariant under such rescaling. So the simplest possible object is a certain matrix of scalar products between left eigenvectors and right eigenvectors, and this is indeed invariant under this rescaling. And this object will also be a topic of Gernot-Ackermann's talks. And so he will tell about some beautiful mathematical properties of this matrix. And we looked at the diagonal elements of this matrix on this model introduced by Rajan and Abbott. And this is what we discovered. So starting from the initial matrix, which was considered by Sampolinsky, so this was just this stochastic part. We look at the distribution of the eigenvalues, and also on this diagonal element of this overlap matrix. And indeed, we see that the introduction of this matrix with constant connections produces some outliers, and this excitation-inhibition balance brings them back. Moreover, you can see that the position of these eigenvalues are exactly the same here and here. But when we add this matrix with constant connections, and we impose the excitation-inhibition balance, although these eigenvalues are brought back to the circle, they have much increased value of this diagonal element of this matrix. Okay, so you can see that there are no free lunches. So even though we solved one of the problem, the price that we paid is in the properties of eigenvectors. So all the rubbish is put into this non-orthogonality of the eigenvectors. Okay, but you may ask, so what? What does it mean? Or what's the message of it? So now let me tell you about two properties that the non-orthogonality of eigenvectors may play an important role. Okay, so you know that brain is not a static object. It can learn, it can forget, and it does so by readjusting synapses, creating new connections, and so on. And the dynamics of matrices is quite a complicated problem, and unfortunately not much is known about. But fortunately, if the change of the parameters of this matrix, which corresponds to readjusting the weights by learning, if this change is small, then we can expect to use perturbation theory and rely on the first order of the perturbation theory, which gives us the correction to the position of the eigenvalue, and the upper bound, which comes from the Cauchy inequality here, the upper bound is exactly given by the square root of this diagonal overlap, the diagonal element of this overlap matrix. And it turns out that this number already appeared in the community of people doing numerical analysis in the 60s, when it was quite crucial to estimate the precision of the calculations. And people were working, like, for example, precision with 10 to minus 10. But it can happen that if you are using your diagonalization algorithm, you are working with this precision 10 to minus 10, but your eigenvalue can be conditioned so badly in the sense that this number is so big that you are losing some digits with your precision. And you need to deal with that or be okay with this loss of precision. So you can see that the diagonal elements of this overlap matrix, they control the stability of the spectrum, and eigenvalues with larger numbers can be perturbed much more than the others. Okay, so let us also consider dynamics of this neural network. Yes?
Can you try to plot trajectories of this eigenvalue with respect to the class perturbations?
With respect to the class?
Consider some class of matrices P and plot the trajectory of the eigenvalue.
Mm-hmm.
Like the orbit of it.
Yeah, I see what you mean. Yeah, you can do this. Yeah. Yeah, but I mean the trajectory depends every time on the realization of your perturbation.
But it happens really fast. So it
I'm
happens
curious
a lot.
if you can say something about the classes of P by investigating the orbits of or trajectories of lambda. Okay.
Okay, so let us consider the dynamics of this neural network, but close to the fixed point, which was stable at the beginning. It may happen that even though the eigenvalues of this weight matrix, which govern the asymptotic time dynamics, are the same, the early time dynamics of the system can be completely different. It may happen that at the beginning of the dynamics, the squared norm of the solution, which is also a squared Euclidean distance from the fixed point, can increase even though the system is stable. This is quite a peculiar behavior. People were discovering this in different communities independently, and it became important in the context of neuroscience because it was proposed, this amplification of the squared norm, or this drifting away from the fixed point at the beginning of the dynamics was proposed as a mechanism of amplification of neural signals, in the sense that if a neuron is excited by some external source, its activity is kept in a large value for a long time before it starts decreasing. But at that time, another excitation from a different neuron can come in.
But this cannot be the linear dynamics. This is no longer the linearized dynamics, because that would either explode or
It is a linear dynamics.
No, it can't be.
This?
If you have sort of exponential contributions of the
asymptotically.
At short times.
Yeah, exactly. So the long time is indeed captured by these eigenvalues. So the slope is the same.
Long time, long time.
Yeah, exactly. So yeah, as Reimer has pointed out, the problem is very easy to solve by matrix exponential. And looking at the squared norm of this solution, we get a product of two exponents. And if we go to the eigenbasis, we obtain the contribution both from the eigenvalues and from the eigenvectors. And the non-orthogonality of eigenvectors couples all the eigenvalues together in a very non-trivial way. And this dynamics is simplified a lot when the matrices are normal, because it decomposes into each eigenmode independently. And if we average over all initial conditions, we can get rid of this x0, and we obtain exactly that the coupling between the eigenmodes is this overlap matrix between the eigenvectors. And this amplification of the trajectory comes from the fact that the eigenvectors are not orthogonal, and there is no upper limit on the value of the scalar product. And we observe that it is typically a large number, and it grows with the size of a matrix. And also, we are projecting our initial condition onto a basis which is not orthogonal. So let us take our initial condition, the red arrows, which are in the orthogonal basis, in a canonical basis, and we want to project them into a basis which is not orthogonal, and we can see that the coefficients of the projection can be much larger. So this is why these terms can be responsible for this amplification at the early time of the dynamics. Okay, so you can see that indeed the eigenvectors can play an important role, but the question is whether we can observe this in the model, whether we can observe this transient amplification in the model of Rajan and Abbott. So we went to a computer, we did some simulations, and we clearly see that that if we add this matrix of constant connections, which differentiate between excitatory and inhibitory neurons, and we also want to keep this excitation and inhibition balance, then we observed large amplification of this squared norm, and it also has a very peculiar behavior, namely it oscillates quite often, and it can have an interpretation of an interference between the eigenmodes. And we are thinking that this may be of interest for people in neuroscience. Then we also discovered that if we looked at the activity of each neuron independently, and if we don't have this matrix of constant connections, then the activity is more like random. So we don't see any structure. But if we put this condition on the neurons, then we see that they behave in a very collective way. This activity does not decay for a long time, which is also a result of this transient amplification. But unfortunately, we are not the first ones to see this. Turns out that a group from France has observed this in the full nonlinear dynamics of this Stompolinski model with the condition introduced by Rajan and Abbott. Okay, so the question is whether we can say something more than just numerics, and the answer is yes. We can use some tools from random matrix theory and pre-probability to get some quantitative estimations on the numbers, on the values of this matrix of overlaps. So today I would like not to bore you with all the mathematical formulas, rather than to have a general impression. And if you're interested in the mathematical details, they are stored in our paper. And yeah, to summarize this talk, so we try to convince people in neuroscience that there is much more to discover in models of neural networks beyond the eigenvalue analysis. especially regarding the early time dynamics. The inclusion of this excitatory-inhibitory balance can lead to a very high sensitivity of spectrum of the matrix to perturbation, and we also see this transient amplification. And when we discovered this, we had a problem how to interpret the results. Because on the one hand, if a brain can be described by this model, this means that a very small change in the parameters of the weights between synapses can cause one outlier to go out from the main bulk of the spectrum, and then the brain can behave chaotically. But on the other hand, it is much easier to readjust the whole spectrum by tuning small parameters. So in the sense that learning can be cheap. And it turns out that this is quite a long-lasting dilemma in the neuroscience. It is called a stability plasticity dilemma, and to the best of my knowledge, it's still not resolved. And we are working more on elaborating our quantitative results regarding these models and the properties of eigenvectors. So this is all. Thank you for your attention.
We finished a bit earlier. So we still have a lot of time for questions. And Jan?
Is there any, I would say, intuitive understanding why these rules increase these non-orthogonality factors and these rules imposed by that you described?
So one of the heuristics is that imposing this matrix M often puts a lot of numbers to the system, but it does not change the spectrum. So this information must be stored somewhere else. So it must be in the eigenvectors.
Okay, this I buy, but why it should drastically increase this? It's not clear. But yes, it's stored in some way. But you show that this overlaps become 10 times larger.
That's right. That's right. So you can look at this problem, I would say, from the reverse. Namely, starting from this, we can do a very small change to bring all these eigenvalues back. So it's a very, I would say, fine-tuning to get the correct behavior. But the price that you pay is that you can easily undo this.
So it's in this sense, you have sensitivity, and then I understand.
Just to put this into perspective, because you started from the RNN consideration, right? So this all actually considered the output of the neural network dynamics, correct? So the conclusion is here that basically this output decays towards zero, but it's not how they work in practice, because you always, it's recurrent system, so you always feed this with some data. So maybe it would be interesting to see how this thing behaves as an open system.
That's right. That's right. People in neuroscience are doing this. So they are feeding their continuous time networks with some data, and they see how they behave. And more interestingly, they indeed can train them to do some tasks.
Because static generation doesn't follow by just initiating neural network and letting it go, right? You constantly feed this with data.
That's right.
More questions? Maybe I would make a small comment. So generally, I think what we would like to stress in the so-called Krakow school of eigenvectors is that we believe that when one looks at non-normal matrices, one has to change the paradigm. Traditionally, random matrix theory deals with eigenvalues, because this is how people started. And then when people encountered non-Hermitian random matrices, non-normal, they also started with eigenvalues, because this was already quite difficult. Okay? What they somehow missed is the eigenvectors, And I would like to recall you that for 50 years after Geneva paper, nobody has written the proper algebra equations for the evolution of eigenvectors for the Gaussian, for the simplest Gaussian ensemble. This was done actually only 2 years ago by two groups. So this evolution shows precisely that when you look at any kind of analysis, dynamical analysis or stability of analysis when matrices are not symmetric, eigenvectors are absolutely crucial and generally they're also driving, they are more important than eigenvectors, they are driving they are driving the evolution, and we believe that since in practice most random matrix systems are not normal. Okay, when we look at the networks, the links have arrows. So there is a causality. We believe that this is a really very important issue. Please.
Maybe I have a question on this, because what's the situation? Have you looked at this? If you have sort of a matrix which has you can always decompose a matrix into a symmetric and anti-symmetric part, and when it has a bit of a symmetric part, however small, does that immediately fall back to?
Yeah, we didn't look at it, but this decomposition is always based on normality. Okay?
Yeah.
If both could be, matrix is normal, if both guys could be diagonalized by the same transformation. So this is, but a small amount of normality already wrecks the havoc in the dynamics.
But for the Sompolinsky-Križanti result, they start with totally uncorrelated forward vectors.
Yes.
And if you increase correlations, might be interesting.
Yeah, actually, Jan has written a paper on the number of equilibrium points of this model, how they change with the symmetric parameter, and indeed there is a transition between symmetric and asymmetric.
But the issue of really dynamics is much more subtle.
Okay, so let us thank the speaker again.